Why don't satellites and other spacecrafts launch straight up so they could reach celestial bodies above us, so to say? While it may seem reasonable on the surface, it's simply explained by the fact that all bodies in the solar system lie on the same plane and the system is nearly flat, specifically the ecliptic. However, this inquiry would get us to wonder why satellites are not sent straight up and out of the solar system. To answer this question lies in the laws of motion and the immense amount of energy it would take to send a spacecraft at such a high speed. To break out of the gravitational pull of the Sun and escape its orbit, a tremendous amount of thrust would be required. It would not only be costly, but unfeasible. Also, the laws of motion dictate that it takes more energy to go straight up than it does to go at an angle along the plane of the solar system. So let's explore together why this isn't as trivial as it seems. There are three primary reasons for this. 1. Doing so would require the satellite to cancel out its motion in the direction of Earth's orbit, which would use a great deal of fuel. 2. Most of the interesting stuff in the solar system lies in the plane of the solar system, so it is more practical to send probes horizontally along that plane. And 3. A probe sent straight up and out of the solar system is unlikely to find anything significantly interesting. At the same time, it is possible to send a probe up and away from our solar system, provided that enough fuel is used to cancel out the current velocity of Earth's orbit. Such a mission was attempted with the Voyager probes, which were sent out of the solar system to explore interstellar space. It is also possible for a satellite to be sent on a trajectory that is not strictly perpendicular to the plane of the solar system, but rather gradually moves out of it. This way, the satellite can use less fuel and still eventually leave the solar system. Overall, while it may seem more logical to send satellites and spacecraft straight up, this is not the most efficient way to explore our solar system or to reach celestial bodies beyond it. Instead, satellites are sent along the plane of the solar system or on trajectories that eventually lead out of the solar system in order to conserve fuel and make the most of the resources available for exploration. Earth's orbit. One should pay attention to the fact that Earth is orbiting in the ecliptic plane at a velocity of approximately 30 kilometers per second. That being said, whatever is thrown away from the planet will traverse at a speed of the original velocity added to the planet's orbit speed. To give an example, when you launch a ball from a moving train, the ball's speed is the combination of the speed at which it was thrown and the train speed. To launch a space probe vertically beyond the plane of the solar system, fuel must be burned to counteract the satellite's movement in the direction of the Earth's orbit. Then, the probe can be accelerated vertically, lifting it out of the ecliptic. Launching a probe beyond the boundaries of our solar system will require a tremendous amount of thrust. To achieve the desired velocity, multiple rocket stages may be employed. The initial stage uses rocket motors to give the space probe its initial boost, allowing it to escape Earth's gravitational pull. The second stage uses hydrogen-oxygen engines to sustain the spacecraft's momentum for a long duration of time. Finally, a third stage may be used to accelerate the spacecraft to its final destination. After the fuel runs out, the spacecraft needs to rely on its momentum to reach its destination. Due to the complexity of launching a spacecraft beyond the boundaries of our solar system, it is essential to have a thorough understanding of orbital mechanics. Different trajectories and fuel combinations must be considered when designing a mission. By understanding the basics of orbital mechanics, a mission can be tailored to best suit the desired outcome. Fuel problem. To go beyond the boundaries of the solar system, the space agency responsible for the mission would have to consider the logistical challenge of fueling the probe, increasing its mass and thus the associated cost. It is evident that such an endeavor would be a costly undertaking. For some perspective, let's calculate how many gallons of fuel would be needed to travel to the Moon, the closest body to our Earth. The Apollo mission to the Moon in 1967 was powered by the Saturn V rocket, needing around 950,000 gallons of fuel to escape Earth's atmosphere alone. This consisted largely of 203,400 gallons of kerosene fuel and 318,000 gallons of liquid nitrogen. with the successive stages carrying further supplies of liquid hydrogen. Nearly 50 years later, advances in space-age technology have enabled the SpaceX Falcon 9 to power its crafts with much less fuel. Here, kerosene, which has higher energy per gallon, is used instead of liquid hydrogen, and the Falcon 9's first stage requires 39,000 gallons of liquid oxygen and 24,000 gallons of kerosene, while the second stage needs 7,300 gallons of liquid oxygen and 4,600 gallons of kerosene, making a total of only 75,900 gallons overall. These numbers illustrate just how significantly the cost of space exploration has decreased over the years. The development of more efficient and cost-effective fuel sources has been one of the primary factors in this reduction. For example, SpaceX's current reusable spacecraft design has made deep space exploration much more achievable, as each mission can now be undertaken with considerable fuel savings. This opens up new possibilities for space exploration and the development of space-based projects in the near future. Space agencies hope to use this technology to propel space probes further into the cosmos. With the goal of eventually exploring interstellar space, researchers are seeking to develop rockets powered by nuclear electric propulsion or antimatter propulsion. These engines would be powerful enough to get spacecraft to the outer reaches of the solar system, providing exciting and in-depth opportunities for space exploration. The solar system is mostly arranged in a plane, making it more logical to send probes along the same plane when exploring. This plane contains the majority of the components that we wish to investigate. Therefore, it is advantageous to send probes in a horizontal direction within the solar system's plane. Launching a probe vertically out of the plane of the solar system is unlikely to yield interesting discoveries, but if it continues beyond, it could eventually reach the Oort cloud. It is uncertain where the limits of the Oort cloud start and finish. For example, Voyager 1 spacecraft is traveling at a rate of 1 million miles a day and is projected to take 300 years to reach the Oort cloud. We have previously launched probes out of the solar system in an upward direction. The probes have sent back data which helps scientists understand the makeup of the outer reaches of the solar system. As we learn more about the Oort cloud, it is possible to develop technology to send probes out of the solar system and explore beyond. These missions could help us answer some of the questions we have about interstellar space, and possibly even help us understand the origins of our solar system. It is an exciting time in space exploration, and one can only imagine the many possibilities that lie ahead. Before we continue with the Ulysses mission, be sure to stay tuned afterwards if you haven't seen our earlier release on why planets orbit in the same plane. Ulysses mission. And here comes Ulysses mission. Ulysses was launched in 1990 on a mission to fly over the poles of the Sun. It was jointly launched by NASA and the European Space Agency (ESA). Its main objective was to traverse the Sun's orbit and study it from all angles. This would take the probe to unexplored areas, as previously all the probes had stayed in the same plane as the planets. Ulysses had to alter its orbital inclination in order to depart from the solar plane, so it flew to Jupiter as normal and received a gravitational boost to tilt its plane perpendicular to the solar plane. The trajectory of both Ulysses, Voyager 1 and Voyager 2, are angled away from the ecliptic plane, Ulysses at 35 degrees and Voyager 1 and 2 at 80 degrees. This means that the paths of these spacecrafts are slanting as compared to the plane of the solar system. Ulysses' mission objectives were to map the solar wind and its variations, study the Sun's polar regions, and investigate how the Sun's solar wind affected the environment of the inner solar system. In addition to this, Ulysses also measured the interstellar dust particles and its interaction with the interplanetary medium. Ulysses successfully completed its mission and went on to provide us with valuable information about the solar system and the interstellar medium. Its discoveries have given us a greater understanding of how the solar wind interacts with the planets, the environment of the inner solar system, and the interstellar medium. Ulysses spent 4 years of its 12-year mission in an orbit outside the solar system's plane, giving us data that we had never collected before. This data gave us an insight into the size, temperature, magnetic fields, and composition of the interstellar medium, which helps us to better understand the mechanisms that govern the universe. Today, Ulysses is still considered a highly successful mission, and its discoveries have been used to enhance our understanding of the solar system and the universe. We now understand why satellites and other spacecrafts don't launch straight up and out of the solar system. We must consider the complexity of the mission, the huge amount of fuel needed, and there may not be much to explore beyond the solar system's plane. But with new technology and a better understanding of orbital mechanics, we have opened up new possibilities of exploration. One example is the Ulysses mission, which successfully completed its mission, giving us valuable data which we have used to enhance our knowledge of the solar system and the universe. So while the idea of launching a satellite straight up may be intriguing, we now know that this is not the ideal path for space exploration. With each mission we undertake, we are one step closer to unlocking all of the mysteries of the universe.
What's the most popular elementary school project you could think of? Seeds grown from paper? The foam volcano? Whatever it is, I bet that if I ask you to make a list, one of the items that would be on the top of it will be a model of the solar system. If you would recall, these models are basically concentric circles with balls placed somewhere on the circle's circumferences. The balls represent the planets, while the circles represent the orbits. Because of how plain it looks like, one might be tempted to think that this is an oversimplified version of the solar system. I mean, the popular model of the atom is somehow derived from this, right? The exact reason why we call it the planetary model of an atom. And if our star system doesn't really look like that, then I think we did an awful job of naming it, didn't we? Of course, you wouldn't tune into this episode if the answers were that easy, would you? Despite being counterintuitive, the elementary science fair model of the solar system is actually as close to reality as it could get. I know what you think, but that doesn't make sense. We have a three-dimensional space, so naturally, we can expect that every structure in the universe would be in 3D too. Now, I'm not saying that logic isn't right. It does make sense that if we are in a 3D space, then we expect 3D structures. For instance, some stars could experience an extremely strong influence of gravity, causing them to collect together and form a spherical structure that are called globular clusters. They're a common sight in the universe. In fact, in our very own Milky Way galaxy alone, we are bound to find around 150 of these stellar clusters, but they're not the star of the show today. This is all too weird, right? With all the freedom of motion they have, with all the space that is available for them to move about, a lot of heavenly bodies seem to favor moving in a very confined manner. But how and why exactly does this happen? Well, to be able to understand how motion in the universe ends up this way, or at least in the solar system, we need to recall two important concepts in physics. First, we need to relearn angular momentum. I know a lot of our viewers have a pretty strong grasp of a lot of topics in physics, but we here in the channel want to invite more and more people to be interested in science. So for their sake, I'll make a brief walkthrough of what that is. Second, we need to recall how our very own solar system was formed, around 5 billion years ago, back when the sun wasn't even a star yet. Ready? Okay, so here it goes. So angular momentum first. If you know linear momentum, then angular momentum wouldn't be too hard to grasp. Linear momentum is the tendency of an object to move in a straight line. By that logic, we can say that angular momentum is the tendency of an object to rotate. I hope you're not lost so far. Trust me, learning this is really important in understanding the main goal of the video. Now, there are two most fundamentally conserved quantities of motion in the universe. On one hand, we have energy and then momentum on the other. By this logic, we can derive that all momenta are conserved, even the angular one. So okay, angular or rotational momentum is conserved. What does that imply? Say, for example, you have a top that's spinning perpetually. It doesn't stop. It just keeps spinning and spinning. So you can perform measurements on it any way you like. Now, say, for instance, you measure the angular momentum of this spinner at one time. After doing the task, you felt hungry, so you came out for a long lunch, then came back and measured it again. By conservation laws, you want to get about the same value for angular momentum as you did earlier. Angular momentum depends on two factors. First, the distribution of mass in the spinning object, and second, how fast this object spins. Let's relate that with rotational momentums need to be conserved all the time. Since the value of angular momentum is constant because of conservation laws, whatever change in one factor, the other has to compensate. For instance, if the distribution of mass becomes less, say for example the volume of this object decreases, then the rotation has to increase. You can see how this works in ice skaters spinning faster when they draw their hands closer to their bodies. The same works the other way. If the rotation of the object increases, since angular momentum loves to stay constant, the distribution of mass increases. If you know how to make pizza, you would notice that the dough only becomes flat when you make it spin. Can you piece it together now? The answer to why objects in the solar system, or a large number of objects in the universe, seems to favor a flat orbital plane over a volumetric one. If you can't yet, don't worry. That's exactly what we're here to learn. The next thing that we need to learn is the formation of our solar system. How exactly are we going to accomplish that? Let's go back about 4.6 billion years to the past, at a time when the sun isn't even a star yet. Back at a very simple time when the materials that would make our own star system home are still swirling about in a large cloud of dust. But before we take a deep dive into that, okay, back to the beginning of the solar system. As everything in the universe, our small star-centered family began as a huge cloud of molecular dust. Everything was so simple. Particles are just moving about with respect to a common center of mass. The individual particles in this cloud are not stationary. Due to the effects of the very subtle gravitational force about the common center of gravity, the particles are colliding against one another, causing the cloud to have a spin. Like if you could take a spaceship and observe it from a certain point of view, you're bound to see a spinning cloud. This spin is really slow, like extremely slow, but nonetheless a spin. Then, at some point in the past, we don't really know when exactly, but scientists infer that it most probably happened. A massive supernova took place somewhere near the then developing solar system protocloud, causing it to spin way faster than how it initially goes. Remember the pizza dough analogy earlier? Now the cloud of dust is exposed to this kind of tension. We said earlier that angular momentum is a quality that loves to be conserved, meaning if you measure this quantity at some point in time, you are bound to get a constant value. It doesn't change. So when the cloud of dust experienced energy and increased its rotational speed, it had to compensate. The distribution of mass has to decrease. How exactly does that happen? The particles in the cloud are moving farther and farther apart from their common center of mass. The blob that was the cloud of particles earlier becomes flatter and flatter. And voila, we have a flat proto-cloud disk. As time goes by, the continuous spin from individual clumps inside this disk coalesce to form everything that we see in the solar system. The planets, the comets, dwarf planets, and even the sun. I have to say though, some mathematics suggest that it is possible to describe a cloud spin in 4 dimensions in an attempt to understand it better. However, doing this doesn't result in blobs transforming to plates in the end, so it is most likely an inaccurate description. For the sake of discussion, we can ignore that idea, or maybe we can cover it in another video. Stay tuned to find out. Now, okay, we know that generally most of the objects in the solar system are laid down flat, but what about the anomalous orbits? You know exactly what I'm talking about. The odd brother, and formerly the 9th planet of the solar system, Pluto. The X-planet's orbit is what scientists label as eccentric. No, Pluto's orbit doesn't dress up with a weird fashion sense. Not that kind of eccentric. What they meant by it is that the orbit of this celestial body is tilted by 17 degrees with respect to the orbital plane. Besides that, its orbit is more oval than everybody else. It gets moments when it's really close to the sun, and then it gets moments when it's super far from everybody else. Now okay, so the question in everyone's mind, I guess, is our solar system unique? Is our solar system the only star system in the universe to have a preference for flatness? How about you place your bets in the comment section below? Winner gets to see the next episode. Well, you don't have to look very far to see that it's not just our home system that has a planar orbit. See how the asteroid belts form in the outer regions of the solar system? I'm willing to bet that you're bound to see that they too seem to follow a flat orbit. Okay, maybe not entirely because a torus shape is more appropriate, but they are still lying on the same plane, so to speak. Then let's take, for instance, Jupiter and Saturn, our planetary family's 2 big brothers. Both of these planets have natural satellites, which are regular, which means they orbit around the planets in a, surprise, surprise, a plane-like orbit. And while we're at the subject, let's talk about Saturn's rings as well. Notice how in the images, the planet looks like a huge ball in the middle of a CD with an unusually large hole? Scientists infer that these rings have formed in the same manner as the regular moons, through the conservation of angular momentum. In fact, when Cassini took an image of it in 1997, it captured a few smaller mini-moons forming inside the rings, which confirms what we already know about planetary and satellite formation. If you travel far enough into space, you are bound to see that our very own Milky Way also appears to be flat in shape. And if you carry on with your travels and approach the galactic center, you are bound to see a supermassive black hole. Considering how massive these objects are, it is with most certainty that you find an accretion disk around it, another flat formation resulting from a combination of forces in 3D space. Although, not saying that accretion disks can only be found in black holes, okay? Practically anything that's massive enough can exhibit accretion disks around them. Usually you find these around developing stars, neutron stars, binary stars that are eating its twin, to name a few. So there we have it. We are hammered by the irony of the universe. With all the freedom of movement that objects are bound to have, most of them still have the tendency to simplify into a flat, two-dimensional shape. But then again, it's not like the objects opted this to happen, right? We learned that with the right amount of gravity and the desire of things in the universe to keep spinning, the outcome is something we can always guess. There's nothing really special in the formation of flat structures. It's just the laws of nature, specifically the conservation laws at work. And isn't that neat? With our pursuit of knowledge, we have arrived at a point where we can describe most of the stuff that's going on, not just on Earth, but in the universe as well, with rules that we arrived at using observations that were initially done on our home planet. I know that's a lot to take in, but let me just say that every day I am extremely amazed, not just by what we see out there in the universe, but the way we mankind arrived at methods to be able to describe these experiences in the best way we can. To top off today's episode, I want to tickle your knowledge sides a bit and leave you with a question. Do you think there are other structures in the universe that are odd or weird? Structures that are unique in their shape or form? I'd love to know what you think. Leave us your response in the comment section down below. We'll do our best to respond to them, since there's nothing more that we love here than interacting with our avid viewers. And as always, I cannot express how grateful I am to you guys who regularly watch the episodes that we release. We dedicate a lot of work and time in making sure we deliver the best and most awesome content for you. Did you love what we made today? Let us know by leaving a like, or if you're extremely displeased and don't want to hear any of this in the future, which I hope is not the case, leave a dislike. Whatever opinion or insight you have, all of that helps us develop better content for you in the future. And for our friends that are new in the channel, I have a suggestion for you. It's just a suggestion, no pressure. So how about you press that subscribe button? What do you think? I mean, we release new videos every day, and we don't want you to miss any of our content. And while you're at it, why don't you hit up that bell button as well, so that you'll receive a notification whenever a new episode comes up. We make new ones every day. Until next time, stay insanely curious.